Okay, the purpose of this video is to walk you through this Mystery Signal 2 project. Hopefully I can give you some hints and keep you on the right track where this doesn't take a ton of time. I mean, it's going to take a little time for you to work through how to piece all this together, and hopefully what you're hung up on is mainly learning the communication theory, not so much just tweaking the code. All right, so if you have coding kind of problems, hopefully we can get together and solve those. All right, so the approach here is very similar to what we've done before. You're looking at loading this Mystery Signal 2 file, and in that will be a signal down here, R, and a time vector T. Okay, so the things that are different is we are now using square root raised cosine pulses, and you'll need to know these parameters for the match filter step. Okay, so you'll need to know it extends over 10 symbols and the beta is equal to 0.3. There's also this upsample factor P that you use, and you'll have to go through the theory and figure out what to use for the upsample factor on the square root raised cosine pulse. As I'm thinking about it, there's also an offset parameter in the SRRC code. You would just use offset equal to 0. All right, so what we have here is I start with some randomly generated PAM symbols that serve as training data. So that's at the front end of the things that you're trying to decode, and that's to let all the algorithms converge, and so you can extract the real signal. We have 5 blocks, and each block has this framework sequence that you need to detect. At the end of the day, you're going to end up reproducing those 5 frames of 500 characters in length showing up in your output code. All right. Some of the parameters you're going to need to know the symbol rate and the sampling rate. From that, you can get the upsample factor. You also need to know the original carrier frequency is 10.3 megahertz. Okay, so again, when you load this mat file, you will see the variable R appearing and also a time variable. All right, so you're supposed to take R and process that and go through all these steps. Okay, so the very first thing you need to do is actually calculate the intermediate frequency. I think I changed the terminology between Mystery Signal 1 and Mystery Signal 2. I might have called it the carrier frequency, but really, when you downsample, we've gone through this calculation a few times. When you downsample, it also changes. It's effectively using aliasing to change the what appears to be the carrier frequency. So the textbook starts calling that the intermediate frequency, and so let's do that as well. So the variable that we use for that is f0. Okay, and so we know we take 10.3 megahertz. Figure out where that alias is back down to within a sampling rate of 1 megasamples per second. So if you're sampling at 1 megasamples per second, the Nyquist rate is minus 500K to 500K. So you alias down by multiples of 1 megasample or 1 megahertz until you land in the Nyquist interval, and that gives you your f0. Okay, so we've talked about that before. All right, so from there, I want you to use the myBandwidth command to produce a plot that shows the bandwidth of the signal. This is just to make sure you've got things loaded, and you're going to need to know some estimates of bandwidth to tweak some of the parameters. All right, so I have a MATLAB plot that I'm going to give you a brief look at. So when you do that, you should get something that looks like this. Okay, all right. Next, in this step, this is a really pretty easy step. Determine the upsample factor M. This would be the nominal upsample factor, and it turns out the real upsample factor used at the transmitter doesn't match the nominal. So we're going to need some algorithms to take care of that. Okay, it turns out also the real intermediate frequency doesn't match f0. So we're going to use a dual Costas loop to synthesize a local oscillator. We did this in mystery signal number 1. And you're going to end up with 2 phase estimates, theta 1 and theta 2. If you recall, last time we had to tweak the low pass filter, the filter length. All those should be, if you got it working in mystery signal 1 and you use those parameters, I think roughly the same thing should still work. And there's also the mu1 and mu2 parameters that you can play around with. All right, so in this third step, you're going to construct a subplot for theta 1 and theta 2. Remember, we're doing these dual loop things. All right, and so I wanted to show you what that would look like. Part of the problem that we have with when we start using square root raised cosine pulses, it's not as easy to plot the time domain plot and make sense of it. Okay, so one of the things that people get hung up on in working on these projects is to know whether or not you're on the right track. Okay, so here's how you can tell. When you do the phase plot for the Costas loop, you should get a straight line, and of course we know what that means. That means there's a difference between F naught nominal and the actual F naught used at the transmitter. So you should get something that looks like this. The theta 2 estimate can be pretty noisy. All right, but the theta 1 estimate needs to be tracking. So if you see stuff that's wildly varying, chances are your update parameters are too big. Okay, if you see something where theta 1 and theta 2 have a slope, but they just, things still aren't looking right, then chances are your update parameters are too small. So that's just some hints on how to adjust that. Okay, so let me move that back out of the way. In this step, based on your answers, you look at the slope of that line for the theta 1 plot. You're supposed to be able to, and I know you can do this, estimate the frequency mismatch between the nominal and the transmitter based on the slope of that theta 1 line. Okay, so once you have that, you now have generated an oscillator. Okay, in the code we used before, it was called YOSC. Okay, so you have that oscillator. You've recovered that with that algorithm. Okay, so using that, we go through our usual demodulation step. Multiply the signal by YOSC, low pass filter. Okay, so the next thing you need to do is you need to apply the matched filter, because this is now at the receiver. We are the receiver. We've demodulated. We now apply matched filtering. Okay, so we've done that in some of the examples where we just convolve it with the flip version of a raised cosine pulse. Often I don't put that flip left-right step in there because raised cosine pulses are symmetric and flipping them doesn't make any difference. Okay, so from there, you've produced a received signal. You can call it what you want, all right? But from there, I would like to see a bandwidth plot, and this should be back at baseband, so I wanted to give you an idea of what that would look like. So, it looks like the same shape on the plots I showed you before, only shifted back down to baseband. All right, so you're on the right track if after the demodulation step you start to see something that looks like this. Okay. Next, from here, we're going to use the clock recovery algorithm to determine the optimal downsampling times. Okay, so you would paste that code in, you make any adjustments that you might need to make. This is where you'll need to know the nominal upsample factor M that goes into that code. All right, so plug that in and adjust the update parameters. Remember on this one, sometimes you can get those fairly large to make them work, but adjust the update parameters to see a soft decision diagram and tau 1 and tau 2. All right, so your plot there should look like the following. Okay, so it looks something like this, where your tau 1 estimate, there's an offset on the upsample factor. The upsample factor is not quite right at the transmitter. It's different than the nominal. All right, so based on the slope of that line, you can estimate that. We've talked about that in some of the videos. You should also have an eye diagram. The eye diagram should look right in the sense that it's centered up at 3, 1, -1, and -3. It's fuzzy. It's fuzzy because I've added some noise to the signal as well. But there's still a gap. The eye is open. All right, and you should be able to produce a plot that looks like that. Okay, so next, I want you to implement this frame detection algorithm based on correlation. Okay, so it turns out, I thought you'd like the word happily. Maybe there's nothing happy about this, but happily, I think this is a much easier step than what we did on Mystery Signal 1. And the difference is we're working with things that are sampled at the symbol rate, not at the sampling rate. And because we're at the symbol rate, the peaks in the plot are much sharper. So we don't have to worry about this range of values that would work. Okay, if you think back on that, that's part of the difficulty we had with that. All right, so when you turn in your correlation plot, it should look something like this. It might be, depending on your parameters, these peaks point down, and we know what that means. You have to multiply the whole signal by -1. But because your costless loop algorithm converged to some multiple of pi, okay? Some odd multiple of pi, to be precise. All right, so you see there's some pretty sharp peaks here, and if you zoom in, it's only a single value where that's got a peak. All right, so if you can take that, then you know where to start your frame. All right, and so from there, it's pretty easy to run that downsampled step. Okay, to do frame synchronization. All right, so I'd like you to include a plot like that I just showed you in your grade scope report. And from there, once you have where to downsample at, it's pretty easy to quantize your soft decisions and then decode each of the 5 blocks of text. So just let that run, show up in your MATLAB code, capture that, and turn it into your grade scope report. Okay, so hopefully this video helps walk you through this. If you get hung up on the coding steps, of course, let me know. And if you're hung up on the theory, of course, we can talk about that as well. All right, so I know some of you are worried about this online format and how to talk about things, but I think we've established that we can share each other's screens. I can look at your code. I can answer questions that you might have. All right, so good luck with this, and we'll be talking soon.